Hello everyone, welcome to the session. So in this particular video, I will talk about the basics of heap data structure and when this data structure came into picture. Okay, so let's get started. We'll try to understand each and everything step by step. So as this is the very first session on the basis of this heap data structure, so I'll try to discuss only the basic part of that, okay? And in the upcoming videos, you will see the advanced part of that, followed by the interview-based questions as well, okay? So let's get started with a very fresh new topic, which is related to heap data structure. Fine? Heap data structure. So here, whenever we are talking about this kind of a data structure, the very first thing that you have to keep in your head is that it's a kind of a tree-based data structure, and that too a complete binary tree. So it is a portion inside a complete binary tree. So in order to understand the heap data structure, you should have an understanding of what is a tree or what is a binary tree first of all, and then what is the meaning of a complete binary tree. So let me talk about basics of this binary tree and then complete binary tree first, and then step by step we will move towards this basic heap data structure. Okay, what do we mean by first of all the tree? So tree is a kind of a data structure, okay, which is in a unordered fashion, which is not in a linear fashion. So usually in a practical real life example, what is in a tree? A tree is something where we will be having the root node at the roots are there at the very end, right? And leaves are there. I'm not good with drawing, so please please don't pay attention towards my drawing, but let me just want to give you one example here. So for example, this is a tree where above one is the leaves, right? Leaves are there. But in actual data structure, whenever we are discussing about a tree-based data structure, the order is completely reversed. So what do we mean by that? In our tree-based data structure, the root node is at the topmost node. So we usually say that whatsoever be the topmost node that we have is a root node, okay? And root node is there, and after that we will be having a lot of internal nodes are there, and finally at the very end we used to have the leaf nodes. So usually in practical real life examples, whenever we will see tree, leaves at the top, right? But in our tree data structure, leaf is at the bottom. So these are something which we called as a leaf node, leaf nodes. So leaf nodes are something in data structure which is not having any further child node. So which is not, no child node is there. If you can see here, for all these three nodes, four nodes, we don't have any child. This is something which we called as a leaf nodes. And in between the root node and the leaf node comes a internal nodes. So we will be having a root node, we will be having a leaf nodes, and then in between root node and the leaf nodes, we will be having the internal nodes. So this is the portion of a tree data structure, right? This is a part of a tree data structure. Okay, so this is something that we have. Then I'm saying, so this is called when I'm saying complete binary tree, so we have understood what is the meaning of a tree. Now the next question is, what is the meaning of a binary tree? So when I'm saying binary means two. It means that whenever you will heard this term called as binary tree, it simply indicates that either we will be having the number of child nodes. The number of child nodes will be either 0 or 1 or 2. Binary tree says that at most the node is having two child nodes. At most, the node is having two child nodes. That is the simple meaning of a binary tree, right? So either when I'm saying at most, it means ज़्यादा से ज़्यादा, right? In Hindi we used to say ज़्यादा से ज़्यादा, means either it can have 0 node, or it can have 1 node, or it can have at max 2 nodes are there. Okay, so now we have understood. So when I'm saying this kind of a tree, this is a binary tree, because here if you will see, every particular node is having at max 2 child nodes, right? Every internal node is also having at max 2 child nodes. Then there comes a concept of what is the meaning of a complete binary tree. So we understood what is tree, right? We understood what is a binary tree also. Now here comes what is the meaning of a complete binary tree. But before moving towards that part, let me talk about a full binary tree. So there comes three concepts which can be asked in an interview as well, and people generally get confused between these three things. That is, first of all, what is the meaning of a full binary tree? After that, we will move towards the complete binary tree. So when I'm saying full binary tree, it says that apart from the leaf node, please try to understand my statements which I'm saying here, that apart from the leaf node, every particular node is having the two child. That is for sure, that every node, sorry. So what is full binary tree says? That every node has two child nodes apart from the leaf nodes. So apart from the leaf nodes, every node has two child nodes. What is the meaning of that? The simple meaning is that here if you will see, for example, this kind of a tree. Here if you will see, every particular node, apart from the last level, which is the leaf node that we have, right, is having a two child nodes. This is something which we called as a full binary tree. So here also, if you will observe, this is also known as a full binary tree, which I have created at the very first time. Okay, fine. Then what is the meaning of a complete binary tree? So there comes some conditions now. So whenever we are talking about either a full binary tree, so full binary tree is also pretty much clear to everyone, I am expecting. Means simple meaning is that all the nodes will be full. That's the meaning. There should not be any empty node. For example, if there is anything like this, then it will not be categorized as a full binary tree. Now, whenever I am talking about something called as complete binary tree, and then I will talk about another term called as almost complete binary tree. So there comes some conditions now. Complete binary tree. So what is the very first condition? It says that the very first thing is that when this is something which we call as a level. So this is by default level number 0, or you can start with the level number 1. Anything you can say. I am numbering it as 1. This is level number 2, and this is level number 3. So the very first condition of CBT, in a short form we can call it as CBT, complete binary tree. So the very first condition of this CBT says that whenever you are filling any node, the upper level should be completely filled up, then only go towards the lower level. So what I am saying is that the very first thing is that after completion of first level, then only after completion of first level, then only I would say move towards the, 2 child nodes. Then only move towards the 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 2 chi filling of next level. Filling of next level. This is the very first thing. Second thing, it says that whenever you are filling a node, always left part should be filled up first. So after completion of left side node, then only go for the completion of right side node. Right side node. So here there are two things. One is something which we called as that after completion of first level, then only we can move towards next level. And the second thing that we are saying is that once we will be able to fill the left node, then only we will be having the opportunity to fill the right node. What is the simple meaning of that? Just try to understand. For example, this is a node that I have, and I am saying that is this a complete binary tree? So complete binary tree, first of all, can be a full binary tree as well. So complete binary tree says that either I will be having all the nodes as completely filled up, means every node will contain that 2 child nodes. Every node will contain either a 2 child node, or it can contain maybe the 1 child node as well. It will be pretty much fine for me. So it gives the more flexibility. Complete binary tree will give the more flexibility as comparable to the full binary tree. Full binary tree strictly says that I required 2 child nodes only. Either I will require 0 or I will require 2 child nodes. So here if you will see in the second level, they will be having every node is having 2 child nodes. In the last level, no particular node is having the child. But CBT says that it is fine for me. Either you will be having a 2 child nodes or you will be having a single child node. But there comes a condition. What is that condition? Is that you should follow some pattern while filling the nodes. The very first pattern is that it should not be like that there is space in the upper level of the nodes and you are filling the next level. For example, here if you will see, I am filling like this. So I am filling like this. Now if you will see, there is a space here to fill the node. This is at the present level, but I am not filling that. So this is not a CBT in that sense, because first condition itself is not valid here. Here if you will see in the next part, this is also not CBT. If you will observe, this is also not CBT. Why? If you will observe, the second condition is violating here, which says that, okay, here if you will see, first condition is fine. The present level is having complete nodes, then only it is going towards the next level. But here, the left side is not completely fully filled yet. Here if you will see, there is a space. There is a space and we are filling this particular node. So this is also not a valid CBT. So both of the conditions will be satisfiable. Yes, if I will fill like this, like this, so present level will be completed. Now when I'm moving towards the next level, I'm filling a left side node first and then I'm filling a right side node. Here if you will see, this is a valid, I would say, CBT, because both of the conditions are satisfying. But now, is this a full binary tree? No, because full binary tree says that every node should have a 2 child nodes. But here, the right side node is not having a 2 child nodes. So this is not a valid full binary tree, but it's a valid CBT, because both of these conditions will be satisfying here. Now there comes a concept what is called as almost complete binary tree. Almost complete binary tree. It says that, so here if you will see, this is also a valid CBT and then this is also a valid CBT, like this, right? This is also a valid CBT. But this particular tree is also comes under the category of a full binary tree, right? This also comes under the category of a full binary tree. Now, when I am talking about an almost complete binary tree, it says that I never ever encounter this kind of a situation where I am having always the two child nodes. Always and always, I will be having only a single child present at the last level, right? So, that is a valid CBT, but that is also a almost complete binary tree. For example, here this is also called as a almost complete binary tree. So, what is the meaning of that? That always a node is having a single child at the leaf node. Simple thing that you need to understand. Now here again, if you will observe, these two conditions will be satisfiable. Whatever conditions I have written for CBT is equally valid when I am talking about a full binary tree or when I am talking about an almost complete binary tree. But if you will observe here that CBT is a flexible version which allows, I would say, full binary tree as well as which will allows almost complete binary tree. Can I say? After understanding the explanation of the same, CBT is very flexible binary tree, which will says that it is fine for me if it is a full binary tree, meaning it's a strict version, meaning that every node should have two child nodes. Almost complete binary tree, it's again a strict version which says that the last level node should contain a single value or single child node, right? So composition of both of them, either it be a FBT or ACBT, both will compose of CBT. So CBT is a flexible version, I would say. Now, whenever we are talking about the heap based data structure, it's a complete binary tree. It's a kind of a data structure which says that after completion of first level only, we will move towards the next level while filling the nodes. Secondly, after completion of left side node only, then only we will move towards filling of the right side node, right? Okay. Now the next important thing that you need to understand here is that try to understand this part also. For example, here I am having the nodes. These are the nodes that I have. Okay, so whenever we are talking, how many number of nodes we have? 1, 2, 3, 4, 5, 6 and 7. Number of nodes is equals to 7. How many number of levels we have? Level number 1, level number 2, level number 3. By default, it will start from 0, 1 and 2. But in total, how many number of levels we have? 3. Suppose I am representing that value as 3. So K indicates the number of levels here, number of levels in a tree, and N indicates the number of nodes in a tree. Okay, number of levels and the number of nodes. Now there are some important properties of a full binary tree or a complete binary tree. The very first property says, so there are some properties, let me write in the next page. The very first property says, so here comes the properties of a, so we are talking always about the full binary tree because we are taking a worst case scenario where we will be having a maximum number of nodes, okay, which I can also refer as a CBT, which is complete binary tree, because now you know what is complete binary tree as well. So here we are taking a version which is having a maximum nodes. So we always talked about a full binary tree type of a version. The very first property says that the number of nodes in a complete binary tree is something which is equals to 2 to the power k minus 1. For example, in the above case, if you will see, what is the value of k? Number of levels, it is equals to 3. So here if you will see, it is equals to 2 to the power 3 minus 1, which is equals to 7. So it means that the number of nodes, in the very first point I want to convey, there is a relationship between the number of nodes and the number of levels in a full binary tree. Here, what is the value of k? You can solve that value as well. So n is equals to 2 to the power k minus 1 if we are writing. So 2 to the power k is equals to n plus 1, right? Now what we can do is that we can say that the value of k will be, we can take log base 2 on both sides, log of n plus 1 base 2. So this is something which we will be able to get as the number of levels. So this k is indicating the number of levels here, right? Which is equals to log base 2 n plus 1. So suppose someone is saying that the value of number of nodes that we have is 63. This is the question I remember was asked in my GATE exam when I gave that. So it's a very simple question which can be asked from you in an interview as well. Because you all know that there is an interview based question series, maybe 10-15 questions will be of MCQ, and then there comes a coding round. So for example, they can ask from you that the number of nodes in a complete binary tree will be equal to 63. So can you tell me what will be the number of levels that a tree will be having? So you can easily calculate by saying it will be equals to log of 63 plus 1, which is equals to 64 base 2. So you should know this relationship, then you will be able to clearly find out. So here it is equals to log base 2 64, and this is nothing but is equals to log base 2. You can easily say it is as 2 to the power 6. So 6 can come up front, so it will be 6 log 2 base 2, and this value will be equals to 1. So 6 into 1 will be equals to 6 only. So you can say that the number of levels will be equals to 6. So given the value of n, you can easily able to find out what will be the number of levels in a tree. Given the number of levels in a tree, you can easily able to find out what is the number of nodes that you have. So you should know the relationship between the number of levels and the number of nodes in a full binary tree or in a complete binary tree. Second important property it says is that almost half of the nodes, if you will take the upper bound of that, will be present at the leaf node. So number of leaf nodes in a complete binary tree or in a full binary tree will be equals to n by 2. Suppose the value of n is 7 here. So if you will say that 7 by 2 and you will take the upper bound of that, it will be nothing but is equals to 4. I am saying that this is something which is you are saying as the number of leaf nodes that I am having in my actual tree. So you will be easily able to find out that. Here if you will observe, this is something which we are saying as the count of the number of leaf nodes. Count of the number of the leaf nodes that we have. So how many number of non-leaf nodes do we have? That will be equals to, if you will take the lower bound of the same. So this is the count of the number of non-leaf nodes. Count of the number of non-leaf nodes that you have. So here if you will observe, if I will take the 7 by 2 lower bound of that, I will be able to get the value which is equals to 3. This is the count of the number of non-leaf nodes which I am talking about. Non-leaf nodes. Do you want to check? Let me check with you. So here if you will see, when I am having the value of n as 7, how many number of leaf nodes we have? Leaf node is the last level node which is not having any child node. 1, 2, 3, 4. How many number of non-leaf nodes we have here? So again, you can count here. So it is equals to 1, 2 and 3. So if you will observe, we are getting the same answer with the formula as well. So this is another property that you should take care in your head, right? the very first property that we have seen is the relationship between the number of leaf nodes and the number of levels. Second property is that how we can count the number of leaf nodes and the number of non-leaf nodes, right? So these are the things that you need to take care of whenever you are talking about a heap-based data structure. So mainly I want to let you know what is the meaning of complete binary tree and what are the properties of that. So in this session, basically I have covered up that. We have seen that what is the major difference between a full binary tree, complete binary tree, and almost complete binary tree. We have also seen what are the important properties of a complete binary tree. Now, because you know what is complete binary tree, in the next important session, we will talk about the actual heap-based data structure, where we will discuss what is the meaning of a Minheap, what is the meaning of a Maxheap, and then step by step we will go towards the in-depth explanation of all of the same, right? So after understanding of the basics of heap data structure, today is the right time that we should talk about that what are the different kind of heap data structures that we have and what is the meaning of that. Okay, so majorly whenever we are talking about a heap-based data structure, we have two different types. One is something which we called as a Minheap. Okay, Minheap tree that we will study in our lectures. And another one is something which we called as the Maxheap tree. If you will be able to understand the internals of one of the tree, automatically there is a very minute difference between the other these two one. So you automatically will be able to understand the another one as well, right? So one thing that we have already understood, that whenever this heap data structure will come into picture, this is something which is applicable only when we will be having a complete binary tree. Now, in order to store this nodes of this complete binary tree, which data structure should we use? Should we go for array-based data structure, or should we try something other than that? This can be the question which can be asked from you and from your general understanding of whatever be the array data structure you know. And I think we have covered up pretty well what is array data structure all about. So let's try to understand first of all this thing, that what should be the storage of the Minheap tree or the Maxheap tree, and why is that so? So usually, suppose whenever you are having one tree, for example, this kind of a tree is there, right? This kind of a tree is there, where you will be having some data like A, B, C, D and E. So indexing will happen like this: 0, 1, 2, 3 and 4. What I am saying is that the left index value will be equals to 2 into I plus 1, and the right indexing will be 2 into I plus 2, right? If you will observe, what is the value of I? I is the upper parent index. So here if you will see, parent index is 0. So that's why you will be able to get 1 here and 2 here. For this D, what is the parent index? It is 1. So 2 into 1 plus 1 is 3. 2 into 1 plus 2 is 4. Similarly, if suppose you want to get the index of, suppose I am saying what is the index of this particular node, whose value will be equals to, suppose F. So you can say it will be 2 into 2. So because the value of the parent node is 2, so it will be equals to 2 into 2 plus 2. So 4 plus 2 is 6. So it should be stored at 6th index. But if I will create this kind of a architecture, can I call this as a valid CBT? Can I say that this is a valid CBT? So the answer is no. Why? Because second condition is violating. This particular part, the left part is not filled up, and we are directly jumping towards the right side filling. So it's not a valid CBT, right? So let me take one valid CBT now, which is A, this is B, this is C, this is D, this is E, this is F. Okay. So A, B, C, D, E and F. So what is the array index that we have here? 0, 1, 2, 3, 4, 5, right? So what I'm saying is that I can store the same thing, the nodes that I have in this particular kind of a data structure, 0, 1, 2, 3, 4 and 5. So this is the index of the array that I have, and now I can store all the values inside this, A, B, C, D, E and F. Now suppose we don't have a condition of CBT. At that point of time, suppose you will be having this kind of a structure like this. This is something which we called as a skewed tree. So if you will be having a skewed tree, at that point of time, suppose this is A, this is B, this is C, this is D. Array index will be 0, right? Starting from 0. What will be the right index? 2i plus 2. So it will be 2. Then what is this index? 2 into 2 plus 2. So it will be equals to 4 plus 2, which is 6. Then this will be 2 into 6 plus 2, which is equals to 14. Meaning that if I will use the array data structure to store this particular tree, I require the indexes starting from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 8, 9, 10, 11, 12, 13, 14, right? 15. So here, if you will observe, I am having A at the 0 index, I am having B at the 2 index, I am having C at the 6th index, and I am having D at the 14th index. Now here if you will observe simply, there is a lot of wastage of space, right? When I am using a array based data structure to store the elements. How I am getting these indexes? Same formula. If I want to calculate the left index, I am using a formula of 2 into I plus 1. If I want to go for a right index, I am using a formula of 2 into I plus 2. Now, one thing that you need to note here is that okay, heap is a complete binary tree. And because it is a complete binary tree, so there will be a very less wastage of space. There will be a very less wastage of space when we are using an array data structure. Only when you are using an almost complete binary tree, at that point of time, there will be somewhere, there will be only single node wastage of space. But when we are using other than that, any kind of a tree, specifically I am talking about a skewed tree, which is either having a maximum number of nodes towards the left side or towards the right side, at that point of time, the same array based data structure is wasting a lot of space. So at that point of time, there is another data structure which we called as a linked list, which is basically using the concept of the pointers to store the addresses of the other nodes, can be preferable. But in our task, when I am talking about a heap based data structure, when I am talking about a Minheap or a Maxheap, we will be able to get an idea that okay, because the wastage is very less and we will be able to store the data very efficiently in an array, we can go for the array based data structure for the storage purpose. That is the one of the important thing that you should know. That why we are using this data structure, what's the purpose of that. So I can store now in any of the heap based data structure, everything will be stored inside the array. Why is that so? Because we have seen that very less wastage of space is there. But apart from heap based data structure, we need to again see the different use cases. If there is a lot of wastage of the space, we can go for other data structures, for example, a linked list that we have, right? Now, the next important thing is, what is Minheap? What is Maxheap? So whenever someone is saying or someone is talking about Minheap, it simply says that the parent node will always having the data smaller than the child node. Always. So parent node always contains the data lesser than the child node. That is the simple meaning of a Minheap tree. Means you will always have at root node will contain the smallest element out of all the nodes that we have. Right? This is the simple thing that is given by a Minheap. So root node will always contain the smallest element in case of a Minheap. Now, Maxheap is just the opposite of the same. Maxheap, as the name suggests, that parent node data, I would say, should always be somehow greater than the child node data. That is the simple definition of a Maxheap. Parent node data will always be having a value which is greater than the child node data. So here also I should mention data less than the child node data here in Minheap, and in Maxheap it should be greater. It means that when we are talking about a Maxheap, root node will contain the maximum element or the largest element in your array. So whatsoever be the largest element that you have will be always present at the root node of the Maxheap. So if suppose you want to find out the minimum element in an array using Minheap, how much time complexity it will take? It will take big O of 1, or I would say constant time complexity, because you know that at zero index maximum element will be there. Why 0 index? Because root node will be having the index of 0 in case of a Minheap. Similarly, suppose you want to find out the maximum element in an array using a Maxheap tree, the time complexity will be equals to big O of 1, or it will be equals to constant. Again, if you will observe, this will also be taking a time complexity of constant. Why? Because here also inside an array, we can simply call the 0 index, we can simply call that first element inside the array, which will give me the maximum element in case of a Maxheap tree. So two components that we know, Minheap tree, right, and the Maxheap tree inside a heap-based data structure. Minheap tree will always try to find out the minimum element, right, and there the parent node will always contain the data which is having a lesser value as comparable to the child node, and whenever we are talking about a Maxheap tree, the relationship will be getting reversed. Here the parent node data will always be having a bigger value as comparable to the child node data. So whenever someone is looking for the smallest element, what he can do? He can simply create a Minheap tree, and with the help of a constant time complexity, he will be able to find out that smallest element. Similarly, if someone is looking for a largest element, in a Maxheap tree, he can go and find out that by extracting a very first element or the 0th index in a tree. Now the question comes, it's completely fine that, okay, we will be having a Minheap tree, we will be able to extract the element to get the smallest, and we will be having a Maxheap tree and we will be able to extract the element to get the largest. But the question is, how we can create any Minheap or Maxheap tree? How we can insert any data inside that? How we can delete any kind of a data inside a Minheap or Maxheap tree? Wait, we will discuss all those things in the next upcoming sessions. So I don't want to discuss everything in one go. So this session, I just want to talk about only what is the meaning of a Minheap tree, what is the meaning of a Maxheap tree, and which particular data structure we should use to store these data, to store the nodes that we have, and why is that so. Given a Minheap, first of all, if suppose a new data is coming into picture, how we can do the insertion of the same? In a nutshell, what I want to say is that we will try to discover that how we can do the insertion in a Minheap. So the topic is insertion in a Minheap data structure. Now I hope everyone knows what is Minheap. So we already have understood that Minheap is something where the parent node is always be having a minimum value, and that should be a complete binary tree. So whenever we are talking about any heap data structure, complete binary tree is coming into picture. So whatsoever conditions we have understood for a complete binary tree is always applicable here. Whether I should say or not, you should have that thing in your head. So what I will do is that I will try to create one Minheap here. For example, here I am having a data like this, 10, then I am having 20, then I am having 30, then here I am having 40, then here I am having 50. So this is 50, suppose, then this is 60, this is 70, okay, this is 80, this is 90, this is 100. Let me stop there itself. Now, what is the index number? So index number will by default start from 0 in an array. So 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, fine. So let me try to create one array here side by side so that I will be able to show you that how basically the data is stored here. So as we know that because it's a complete binary tree, right? It's a CBT. It's a complete binary tree. So there is very less wastage of space in an array, and that's the reason we will use an array data structure to store all these elements. So 10 will be stored here, followed by 20 will be stored here, 30, 40, 50, 60, 70, 80, 90 and 100. So this is a kind of a data structure with the help of which I will be able to store all my elements, all the data elements that I have, right? Now, is this a Minheap? Yes. Why? Because here if you will observe, if you will try to see the data of every parent node, it's always be having a value less than the child node. So 10 is lesser than 20 and 30, 20 is less than 40 and 50, 40 is less than 80 and 90, 50 is less than 100, 30 is less than 60 and 70. So whatever relationship I have talked about or whatsoever property I have talked about in a Minheap is there in this, right? Very important thing. Now, again, next important point is that suppose a new data element is coming into picture and that is having value suppose 5. So this is the new, I would say, data element that I have. Okay, this is the new data element that I have, which I want to insert inside this particular tree. Fine. So first of all, one thing that you need to remember is that whenever we are talking about insertion in any Minheap, or so same thing will applicable for a Maxheap as well. But the only difference is that Maxheap relationship is reversed. At that point of time, you will be having a maximum element at the parent node. So we will not specifically differentially talk about the Maxheap again in another video, because every process is same. It's just the conceptual wise you should know what is the difference between a Minheap and the Maxheap. So whenever a new data element is coming into picture, the insertion will always happen at the end. Means 5 will be stored at the right side of 50 at a very first instance. So let me try to denote a new node with some different marker. So this is 5, which is a new node that I have. So what I'm saying is that 5 will be stored initially at the very last index that I have, means at index number 10. That is fine. So now to store that is not a big deal. It's just a constant task. It's not a big deal, right? We know what is the last location that I have, and because the value of n here, if you will see, is equals to, I think, 10. So what I'm saying is that at the value of array of n, the data element will get stored. But now we need to check that after storing this new data element, whether the property of the min heap is retained or not. Whether the property of a min heap is retained or not. Here, if you will observe, when I am adding this 5 here at the end of the min heap, the property of min heap completely gets violated, because min heap says that the parent node, which is 50 here, should be less than 5, because 5 is the child node. But this is not true. This is not true. So we need to make sure that the property should retain. In order to do so, we need to do the swaps now, right? So what will happen is that this 5 will get swapped with 50, because the value of the 50 is greater than 5, right? There is a comparison. There is always a comparison of the new node with its parent node to check that whether the min heap property is retained or not. Now here, if it is not retained, there will be a swap of the values. Because 50 is greater than 5, they both will swap the values. So 50 will come here and 5 will come here. Now again, this comparison will keep on going until or unless I will not reach to the root node. Until or unless I will not reach to this particular node, where I know that on top of this there is no parent. And root node is the one on the top of which there is no parent. We all know, right? So now again, 5 will get compared with 20. Here, if you will see, 20 is also greater than 5. 20 is the parent whose value is greater than the value of 5, which is the child node. Again, property is violating. So there is a swap. So 5 will come here and 20 will come here. Now in the next iteration, what is the parent of 5? It is 10. So 10 will get compared with 5 and the value of 10 is again greater than 5. So again there will be a swap and 5 will come here, 10 will come here. So now your new tree will look like, now here if you will see on top of 5, is there any parent? No. So it will not do any further comparisons. So here they are doing 3 comparisons, and according to that, I would say 3 swaps also we will do for this particular example which I am talking about, right? So what is the new min heap formed after doing the insertion of 5? It will be like 5 is the parent node or the root node. On the right side, I am having 10. Sorry, on the left side, I am having 10. On the right side, I am having 30. Right? On the left side of 10, I am having 40. On the right side of 10, I am having 20 now. 20 is there. On the left side of 30, I am having 60. On right side of 30, I am having 70. On left side of 40, I am having 80. On right side of 40, I am having 90. I am having 90. Then on the left side of 20, I am having 100. And on the right side of 20, I am having 50. Now here if you will try to observe again. So this is at the 0 index, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Here again if you will try to observe, can I say that this is a valid min heap? 5 is less than 10 and 30. 10 is less than 40 and 20. 40 is less than 80 and 90. 20 is less than 150. 30 is less than 60 and 70. Perfect. So all the combinations that we are seeing in a tree are perfect. It seems to me at least a perfect combination, because every particular parent node, whatever I can see here as of now, will be having a value less than its child node. So I can say that this is now it will become a valid, I would say, min heap tree. Now this will become a valid Minheap tree, because if you will see all the combinations, every parent node has having a value which is less than the child node. So how in an array this structure will look like, if I will show to you. So it will look like, oops, so let me create it again. It will look like this. So I am having 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So it is 0, it is 1, it is 2, it is 3, it is 4, it is 5, it is 6, it is 7, 8, 9 and 10. So it will look like 5 followed by 10, followed by 30, followed by 40, followed by 20, followed by 60, followed by 70, followed by 80, 90, 100 and 50. So this is the complete, I would say, Minheap tree that you will get after insertion of a new element whose name is 5, right? After insertion of this 5 element, this is a kind of a tree which we will be able to get. Now the next important part that we need to understand here is that what is the time complexity required to do that? If you will observe here, initially it is O of 1, because what we are doing is that we are just taking the element and we are trying to fit that element into the last location. But this swapping we are doing until we are reaching towards the root node, right? Now the question is that how many number of levels do we have from the leaf node to the root node? Because at each and every time we will do the same step. We will do the insertion at the very end, and then again we will try to see the number of swaps. We will try to make it a valid Minheap tree, and in worst case scenario we need to reach until the root node, right? So at this point of time, can I ask you, what do you think should be the number of levels do we have? Because the time complexity will be equal to the number of levels, because that many times in worst case scenario you are doing a swap or the comparisons, right? So if you remember, in the last session I have discussed about the relationship between a number of nodes and a number of levels. What is that? That the number of nodes will be equals to 2 to the power k minus 1 for any of the complete binary tree. And I have showed you also that how this relationship is valid. With this relationship, we at that point of time calculated the value of k as well. So here it is nothing but is equals to n plus 1, which is equals to 2 to the power k. If I will take log base 2 on both sides, log base 2 n plus 1, which is equals to log base 2 to the power k. Here k can be moved up front, and the value of log 2 base 2 will become 1, which is equals to log of n plus 1 base 2. So here if you will try to observe one simple thing, that in worst case scenario the value of k in terms of big O is equals to big O of log of n. Can I write like this? Big O of log of n. It means that the number of levels that we have in worst case scenario for a complete binary tree, because heap data structure is completely based on complete binary tree. So in worst case scenario, how many number of comparisons that we will do? The number of comparisons that we will do is equal to log of n. Can I say? How many number of swaps that you will do? That is also equals to log of n. Can I say? Now, these two are the only tasks which are responsible to making a time complexity as a huge one. So, what I want to say here is that time complexity simply depends on these two factors, right? Which is nothing but I would say is the number of comparisons plus the number of swaps. Number of comparisons that we are doing plus the number of swaps in a worst case scenario plus the number of swaps that we are doing. So can I say as a cumulative, this is nothing but is equals to big O of log of n. So what I want to infer here is that I want to simply state here is that whenever you are doing insertion of any new node in case of a Minheap, or you are doing in case of a Maxheap, anything. So what same concept I am telling that it is applicable for a Maxheap as well. So the time complexity required to do that task will be equals to big O of log of n. Why is that so? Because of this relationship that we already have studied, and I just showed you again as well, that how this value of k is big O of log of n, right? So if suppose someone is asking to you, first of all, how we can do the insertion in a Minheap, now I hope that you can tell to them clearly. After that, what is the time complexity required to do the same? That also we can clearly convey with its logical reason of the same, right? What we have seen while talking about the insertion, that in an insertion, whenever we are doing insertion of any new element, at that point of time, I have discussed that the worst case, as well as I would say, and the average case time complexity will be equals to big O of log of n. But suppose if someone is asking to you, what should be the best case time complexity in that scenario? What should be your answer? What will be the best case time complexity in the scenario, in that scenario? What could be the possible answer? Can I say that whenever we are talking about a best case scenario, it will be equals to big O of 1? How? Big O of 1 meaning the constant time complexity I am saying. Why? Because, for example, suppose I am having a Minheap, 10, then 20 is there, then suppose 30 is there, then suppose 40 is there, suppose 50 is there, suppose 60 is there, and now the new element came into picture whose value is 65. Now here if you will try to observe, what will happen? Obviously the 65 element will be stored at the very last index, right? Which is at the 6th index. And here if we will try to see this 65 value is, if it will compare it with the parent, it will say that 30 is less than 65. That's also completely fine. So at this point of time, can I say that after inserting a new element also, this is a valid Minheap, this is a valid Minheap, right? So validity is still retained. So even after doing one comparison, here how many comparisons I did? Just one comparison, right? And only the zero swap. So there is only single comparison which is required in order to get a valid Minheap. So this is a kind of a best case scenario where the time complexity will be equals to constant. Another thing or another question which can be asked from you with respect to the previous video is that suppose the number of elements that in total given to you is somewhere equals to n into 2 to the power n. Okay. So what do you think should be the overall time complexity of inserting any new element inside the Minheap? So already the number of elements will be equals to n into 2 to the power n. What is the overall time complexity required for the insertion of a new element? Now usually people remember or they just cram that, okay, whenever someone is talking about the insertion in a Minheap, the time complexity will be equals to big O of log of n. That's completely fine. But here if you will have to see, if you will observe, when I am saying big O of log of n, this is corresponding to when we have n number of elements in total. Right? When we have n number of elements in total. But when someone just try to manipulate the question by saying that now we don't have n elements, but we have n into 2 to the power n elements in total. So at that point of time, your answer will also get changed. Why? Because now here if you will see, it will be equals to log of n into 2 to the power n. Can I write like this? And this particular term can be written as, this multiplication term can be written as log of n plus log of 2 to the power n. I can take n maybe on the front end side. So it is nothing but is equals to log of n plus n. Considering that this is log base 2. This is log base 2. So now, because when you take this n up front, what you will be able to get as n into log of 2 base 2. And this value is something which is equals to 1. Right? So here if we will see the overall, which particular value is bigger, n is bigger. So overall time complexity will be equals to big O of n for the number of elements that we have whenever we want to do the insertion. So this is for the insertion only. This is for the insertion only, but because we have changed, or the interviewer has changed the number of elements, the total number of elements, according to that our answer will also get changed, right? So that are the few things which I want to discuss before I will go with the deletion part which we want to discuss in this session. That is, what will happen, or what are the steps required for a deletion in a Minheap. Deletion in a Minheap. Okay, so what I can do here is that I will try to first of all create one Minheap. So let me create one Minheap here. For example, here I am having 10, here I am having 20, 30, 40, 50, 60, 70, maybe 80 is there, 90 is there, 100 is there, and suppose 110 is there. I think this is enough. Now here if you will see, is this a valid Minheap? First of all, you need to understand, yes, it is a complete CBT, complete binary tree. It comes under that category, because whenever I am saying Minheap, automatically CBT will come into picture. Secondly, yes, all the values, if you will compare, all the parent value will be lesser than the child node values or child node data, right? Parent data is lesser than the value of child node data. So these two properties are valid, means yes, this is a valid Minheap. Now, in a Minheap or in a Maxheap, as I told you, both of them will go side by side. It's just that when we are taking Maxheap, parent data value will be greater than the child node data. That's fine. Now, whenever a deletion will happen, so deletion will always happen at the root node. Means whenever from a Minheap deletion will happen, it will always extract that 0th index. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, 8, 9 and 10. So what I'm saying is that whenever deletion will happen in a Minheap, automatically this particular node will get deleted. Means in an output you will be able to get, once you will apply any delete operation in a Minheap, you will be able to get the output as 10, because 10 is the node which will be deleted. After that, what will happen? The last node, whatsoever the last node you have, will be copied down to the first node here. So here at 10th position I am having 110. That particular value will get copied here. So 110 will be placed here. Right? So from this particular node, so this will get deleted and this particular node will get copied to the 0th position. Whatsoever be the node present at the very last index. Right? Now here if you will observe, we will be having 110, right? Now this 110 value is, once it will be placed at the 0th position, it will completely destroy the validity of the Minheap property. So now again what will happen? In order to retain that validity of a Minheap, again the comparison will happen. But now comparison will happen towards the two children. Whichever is having a minimum value, it can be present either at left side or at the right side. According to that value, swap will happen. So at every iteration until it will reach to a leaf node, how many number of comparisons will happen? It will be, in case of a deletion, if you will observe, in worst case scenario, it will be equals to, the number of comparisons will be equals to 2 times log of n. 2 times log of n. Why 2 times? Because at each and every time, we are comparing with its left child and with its right child. So 2 child, so that's why 2 times comparison is happening here, right? So at every time we are doing a comparison with its left child and the right child. That's completely fine. And how many number of swaps will happen? Again, we are starting from the root node and we are going until the leaf node in the worst case scenario. So here in deletion, we are starting from the root node to we are moving until the leaf node, right? So root node to leaf node is the worst case scenario, means at this point in time, we are taking a log of n again steps. So the number of swaps will be equals to log of n, right? Log of n. So now let's get started. So 110 will get compared with 20 and 30. 20 is minimum, swap will happen. So 110 will come here, 20 will go here. Again 110 will get compared with 40 and 50. Which value is minimum? 40 is minimum. So 40 will go above and 110 will go here. Again 110 will get compared with 80 and 90. Which is minimum? 80 is minimum. So 80 will go here and 110 will go here. So mainly after doing the deletion, you will be able to get 10 as the output. And how your node will look like now? After the deletion, it will look like 20 followed by 40 on the left side, 30 on the right side. After that, we will be having 80 and 50. So 80 will be on the left side, 50 will be on the right side. After that, we will be having 60 and 70. So 60 will be on the left side, 70 will be on the right side. After that, we will be having 110 and the 90. So 110 will be on the left side, 90 will be on the right side. After that, we will be having 110. So, no, this is deleted, right? This is deleted. So this is the final structure. I think we will be able to get 20, 40, 30, 80, 50, 60, 70, 110, 90 and 100. Yes. So this is the final, I would say, Minheap that we will be able to get after applying one-time deletion. So here if you will observe, we are not passing manually any kind of a data from the user that which particular node you want to delete. Automatically, by default, at each and every time, whenever you're calling the deletion operation, the very first node will get deleted. For example, next time when you will call the deletion, 20 will get deleted, right? And so on. So can I say that always and always, whenever you're calling deletion operation, you will be getting a smallest element at each and every time. You will be getting a smallest element at each and every time. If suppose here you will be having n nodes and you are calling deletion n number of times. So at first time you will be getting a first smallest. So delete, you are calling deletion of the first node. So first time when you will call, you will be able to get a first smallest element, right? For example, here you got 10. When you will call the deletion operation second time, you will be able to get a second smallest element. Now suppose you are storing all these data inside one data structure. Maybe you are taking one separate array, and inside that array, maybe you are storing these elements as well. When you are calling deletion third number of time, at that point of time, you will be getting a third smallest element. Suppose you will be having n elements. So nth time when you will call the deletion, you will be getting a nth smallest element. right? So can I say that the element way that you will be able to get first, second, third, smallest, fourth, smallest, and so on, you will be able to get a array which is a sorted array? Can I say like this, that you will be able to get a sorted array? Yes. And this is what the logic of a heap sort says. Heap sort is another, I would say, comparison based sorting algorithm. Okay, it's also a comparison based sorting algorithm, because here also, if you will see, we are comparing the elements again and again. So it's a comparison based sorting algorithm, right? Where what we are trying to do is that we are trying to delete the element from the min heap step by step, and we are storing those elements in one of the array, and you will see that you will be able to get a sorted array, right, in an increasing fashion, in an increasing order, right? First element will be smallest, then greater, then greater. So in an increasing order, you will be able to get the sorted array. When you are doing the same operation on a max heap, same operation, above operation when you will do on a max heap, again you will be able to get, so when you will do deletion n number of times, right, n number of times in a max heap, so what will happen? Again you will be able to get the sorted array. But now the array fashion will be in a decreasing order. But now the array fashion will be in a decreasing order. Decreasing order. So that is the ultimate thing that you need to understand. And that's the complete idea behind the heap sort algorithm that you should know, right? Now, here if you will see, when I am saying that when we are doing a single one-time deletion, these are the number of comparisons, which is 2 times log of n, because we are comparing towards the left child and the right child. And the number of swaps will be log of n. So what is the overall time complexity? Can I say that the overall time complexity will depend on these 2 factors, which is the number of comparisons plus the number of swaps? So can I say that the overall time complexity will be equals to big O of log of n? Can we say like this? Yes, it will be big O of log of n, right? Now, when I am saying that we are applying the logic of a heap sort, where we are doing the deletion n number of times, at every time you are using a log of n time complexity. Can I say? So you are repeating the same steps n number of times, right? So what will be the overall time complexity? So the overall time complexity is something which will be equals to n log n, right? Big O of n log n. And this is the time complexity of a heap sort algorithm. So whenever we are applying a heap sort algorithm, if someone is asking to you, what is the overall time complexity? It will be equals to big O of n log n. Because we are applying a deletion operation in case of a heap sort, and one time deletion will take log of n time complexity. So when we are applying same operation n number of times, then the overall time complexity will become big O of n log n. That is the overall idea behind the deletion in case of a min heap, right? This is the overall idea behind the deletion in a min heap. The same idea you can apply over a max heap, where again the same thing will happen. Deletion will always happen on the top side, root node. So always in a max heap you will be able to get a greater element. First time, first greatest, second time, second greatest, and so on, right? And again the last element will get moved towards the 0th index, and then comparison and the swaps will happen. In worst case it will lead to big O of log of n. So here if you will try to observe, even when we talk about insertion, time complexity is log of n. Even when I am talking about the deletion, the time complexity is big O of log of n. Even if you will observe at the maximum cases, this is the only time complexity that you will be able to get whenever you are dealing with a heap based data structure. But we will talk about it later when we will in the next video talk about the creation or the building of any Minheap, that how basically a Minheap will be created. In that particular case, when we will discuss about a complete derivation of time complexity, there you got something different time complexity as comparable to this, but maximum operations will be done in big O of log of n time complexity. Only the building or the creation of any Minheap will take big O of n. Apart from that, it's big O of log of n only. But no need to cram anything. You just need to understand it logically the way I'm explaining. And that's the important thing that you need to take from here. And the heap sort also part we have discussed, that what's the intuition. At least we will be now able to get the intuition that whenever someone is saying heap sort, how basically internally things are happening, right? Until so far, we have discussed that in a Minheap, how the insertion and deletion will take place and what's the corresponding time complexity aspect for the same, right? So if suppose some numbers are given to you, just like the given numbers that I have shared with you, I have just randomly written it here. Suppose I want to create a Minheap for the same. So what's the complete process of the same? First of all, what we can do is that we can simply try to write these numbers in the form of a CBT, complete binary tree. So I will start from 75. So it is 75 here. After that, I am having 25, followed by 35, followed by 45, followed by 90, followed by 80, then we have 60, then we have 20, then we have 30, then we have 77, and then we have 88. So these are the nodes that we have inside a tree. What's the index of the same? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is the general tree that we have with its indexing, right? Fine. Now what we want to do here is that whenever we are talking about a Minheap, so here we want to create a Minheap, right? So whenever we want to do a creation of a Minheap, here one thing you need to understand that at the leaf node, there is no as such swap which is required. So we will start from the level above, one above the leaf node. So here we always start from the very last, very last nodes that we have as a subtree. So initially my focus is 90, 77 and 88. This is the last one, right? So here if you will see, are they following the properties of a Minheap? No, because 77 is the lower value. So what I will do is that swap will be required. 77 will be here, 90 will be here. Now here one thing you need to understand is that when we are at the leaf node, or when we are at the last level, that is the leaf nodes, can I say that at that point of time, the number of swaps will be for sure equals to 0? Can I say this statement? Why I am stressing on this part, because this will help me in the future sessions when I will talk about derivations of the same. So I will try to show you, and it's very important derivation, that what is the time complexity of a building of a heap, because many students used to answer it wrong. So in the leaf node, we have observed that the number of swaps will be simply 0, because it's the last element, right, that we have. Now when I'm moving towards the level above than the leaf node, at that point of time, so it will be the maximum number of swaps. Maximum number of swaps, that is at most, it might be the case that is not required, but at most the number of swaps will be equals to 1. Can I say? Right? Just like the way we have seen here. Fine. Now moving ahead. Now this particular data which I have is 45, 20 and 30. Again we need to do the same thing. What is the minimum element? 20 is the minimum one, right? So a swap will be required to make it a Minheap. So 20 will go up, 45 will go down. Perfectly fine, right? All in all, picture is sorted until now. Now let's move ahead towards the next upper level. So here if you will see, I am starting from the below level, which is a leaf node, and I am going step by step towards the root node. Now here if you will try to understand, again go towards from the back side, from the extreme right, 35, 80 and 60. I think this is fine because 35 is lesser than 80 and 60, which is its child node. Coming towards this part, 25, 20 and 77. Here if you will observe, the value 20 is lesser than 25, so there is a swap which is required. Now in this case, again this 25 should get compared with the below child, 45 and 30. And we need to see that whether they are holding a relationship of Minheap or not. Because they are holding, so now there is no need to do the swap. If they are not holding at that point of time, again the swap will be required. So in worst case scenario, the number of swaps required at the above level will be equals to 2. That is at most. At max, we require the 2 swaps in this level, right? Perfectly fine. I believe that everything is making sense. Now, let's move to the upper part. That is the root node that we have. Here, if you will try to understand, again, 20 is having a lesser value than 75. So 20 will get swapped with 75. Now, once the swap will be done, our task is not done yet. Now the 75 will get compared with its 2 children nodes that we have. So here we are having 25 here and I believe 77 is here, right? Yeah. So 25 is the smaller one. So again the swap will be required. 25 will go up and 75 will be going down. Again, so here a swap will be required between 75 and 30 as well, because 30 is having a lower value as comparable to 75. And usually the child node will be having a lower data. So again 75 will go here and 30 will go here. All in all, I think now it is fine. So in worst case scenario, this is what happened in our scenario as well. The number of swaps will be equals to 3. So if you will observe, as I'm moving towards the upper layer, the swaps will also at most scenario will keeps on increasing, right? Take this thing as a note, and I will use this thing as a derivation in my next upcoming video, where I will talk about the time complexity for the build heap. I will take a separate session for that. But as of now, I hope I'm making sense to everyone, right? So what is the final tree which we are making here? So we will be able to get 20 as the root node, I believe. After that, we will be having 25 as the left part. And we will be having, I think, 35 as the right part. Then we will be having 30 at the left of 25. Then we will be having 77 at the right of 25. Then we will be having 80 and 60. So 80 is here, followed by 60 is here. After that, I am having 45, 75. So here I am having 45 and then 75. After that, I am having 90 and 88. So 90 is there, 88 is there, right? After that, we will be having 80 and 60. That we have written, right? So here if I will observe simply, 20 is less than 25 and 35. 25 is less than 30 and 77. 35 is less than 80 and 60. 30 is less than 45 and 75. 77 is less than 90 and 80. So I can say, right, this is a valid min heap, right? I can say that this is a valid min heap, right? So this is a valid min heap that we have. Perfect. So this is how basically any creation of min heap will happen. Where, what are the steps that we have seen in a nutshell? First of all, what we are trying to create is that we are trying to write the numbers as it is in the form of a complete binary tree. In the form of a complete binary tree. Once we will be able to write the numbers in the form of a complete binary tree or in the form of a CBT, after that the process of comparison will start, right? And at this point of time, we are trying to do the swaps according to the situation, that whether we will be having a parent node as a smaller element or not. If we are not having, then we are comparing it with the child node, and whichever is having a minimum element, we are doing a swap with that. So that is the thing that we are trying, starting from the leaf node. We are starting from the leaf node and we are doing the same approach until the root node that we will be having, right? So that is a similar concept which we will move on towards the Maxheap as well. The only difference is that when we are talking about a Maxheap, we will be focusing on the larger element, or we will be focusing on the greater element. I hope that the building portion of a Minheap is clear to everyone, right? Now in the next particular video, what I will do is that I will talk about the time complexity of creation of this Minheap that we have created with this approach. But before watching the next upcoming part, I would request everyone to think over it. What do you think? You have now used know the approach of how basically we can build a Minheap, right? So now using that approach, you just try to see that what can be the optimal time complexity required to do the same. What do you think? Is this order of log of n? This is the answer which is usually given by maximum students in an interview as well. This is the question which can be asked vastly in an interview, and maximum students used to give the wrong answer by saying it big O of log of n. But it's not true. The time complexity to build any Minheap or a Maxheap will be big O of n. And in the next particular video, we will talk about that why is that so. I will talk about the complete justification for the same, so that in future, whenever you are going for an interview and if an interviewer is asking you the same kind of a question, you will be answered it properly with its mathematical intuition behind the same, right? So we have observed one thing there, that whenever we are having a leaf node, so at that point of time, at most 0 swap is required. And when we are moving towards one step above, step by step, the number of swaps will keep on increasing by number 1, right? Taking that thing in your head, now let's get started. So here suppose you will be having a root node, and after that suppose we will be having this kind of a structure of a tree that we have. Okay, so this is a kind of a structure of a tree that we have. Fine. So here let me create more, or it is fine. Consider that at the very last level we will be having, so what I want to create here is that there is some infinite number of nodes that we have. So what I can do is that there is a lot of, you can assume that nodes are there in between, and after that this kind of structure we are creating. Fine. So here you can assume that if this is the leaf node that I have, and consider that at this leaf node the number of nodes will be n. Okay, number of nodes I have at the leaf node I am saying is equals to n. So can you think that what should be the number of nodes present at the level above leaf node? So can I say it will be n by 2, and at next level it will be n by 2 to the power 2, and this series will keep on increasing as I am moving from the leaf node to the root node. At the root node, can I say that the number of nodes will be n by 2 to the power log of n. So here if you will try to observe, we will be having how many number of levels in worst case scenario? This part I think I have talked about a lot in the previous video, that the value of k is equals to log of n base 2 whenever we are talking about a complete binary tree kind of a structure, right? So can I say that the number of levels will be equals to log of n base 2? And if yes, that's the case, so it will be starting from the leaf node to the root node. This is the kind of a situation that we have. Now, whenever we want to calculate the time complexity part, it depends on the two factors: number of swaps, number of comparisons. So here if you will try to see, the major factor or the major contributor that we have is the number of swaps that we are doing, right? In the worst case scenario. So here, if you will try to observe, can I say that the last level leaf node will be n by 2 to the power 0? It is nothing but n only. At that point of time, I am doing only 0 swaps. And when I'm moving ahead towards the upper level, means this level, I am doing 1 swap. At this level, at most I am doing 2 swaps, because here we are talking about a worst case scenario. So we are assuming that we are doing a maximum number of swaps. So when I will move towards this level, how many number of swaps I will do? Log of n, right? So what is the total number of swaps that we are doing here? So can I say it will be equals to n by 2 to the power 1 plus 1, n by 2 to the power 2 into 2, until, can we say it will be equals to n by 2 to the power log of n into log of n, right? This is the kind of a thing that we can say is the total number of swaps that are there whenever we are building a Minheap. Can I say like this? Right? Very simple, right? Now, what we can do here is that we can do one simple thing. We can simply try to take n as common, because what I can feel is that in complete series, whatever I can see here, n is a thing which is common here. So what we can do is that, so here the number of swaps will be this. So capital S can be equals to n into, it will be 0 only. So I can start with 1 by 2 to the power 1 plus 1 by 2 to the power 2 plus it will be 1 by 2 to the power 3 until so on. At the very last level, we will be left with log of n divided by 2 to the power log of n. So this is a kind of a thing that we will be able to get when we are trying to do something called as a common thing for the value of n. So basically, if this part is clear to everyone, then doing n taking as a common is pretty much easy, right? Okay. Now what I want to do here is that I want to form some sort of a GP series here. I want to form some sort of a GP series here. And in order to form that, what I can do is that I can do a division by 2. So what will happen is that I am doing n by 2. So what will happen? So when you will do by 2 here, so it will be 1 by 2 to the power 2 plus 1 by 2 to the power 3 plus 1 by 2 to the power 4 until so on. What we will be able to get the value as, so at the previous, before this position, it will be log of n minus 1 divided by 2 to the power log of n, right? Before this position I am stating. Plus here we will be having log of n divided by 2 to the power log of n plus 1. That is a kind of a thing that we will be able to get. Why we are doing so? Because I want to make one GP series here, and with the help of that GP series, I will apply one formula and I will be able to get the time complexity. So that's the major reason why I'm doing these things. Now what I can do is that I will try to subtract. So this is the equation number 1 that we are getting, and this is the equation number 2 that we are getting here, right? So what I will do is that I will try to subtract the equation number 2 with the equation number 1. So s minus s by 2 will be equals to s by 2. So we are taking a difference, or you can say we are doing a subtraction of equation number 2, right, from equation number 1. So what we can do here is that we can simply try to say s minus s by 2 will be equals to s by 2. It is equals to, we can take n as common, right? So now here if you will try to observe, what we will be able to get is that we will be able to get 1 by 2 to the power 1 will be as it is, plus here if you will see, this is something 1 by 2 to the power 1. So here we did something wrong. Here we will be having the value which is 2 and here it is 3, right? It is not 1. So when we do this thing, so we will be able to get the value as 1. Here we will be able to get the value as 2. Here we will be getting the value as 3. Yeah, now this is correct. Last value is correct. Okay, so now when I am doing the subtraction here, if you will observe, it is 2. So denominator is same, 2 to the power 2. So it is 2 minus 1 is 1. So what I will be able to get is 1 by 2 to the power 2. Here 3 minus 2 will be 1 by 2 to the power 3. Until so on, we will be able to get log of n minus log of n plus 1. So 1 by 2 to the power log of n, right? This is the thing that we will be able to get. Now, after that, what we can do is that I can take, so I am subtracting s minus s by 2. So this will become negative symbol. So I will take this value outside. Log of n divided by 2 to the power log of n plus 1. And I can store everything in one bracket here. Maybe like this. N is outside only. Okay. So until so far what we have discovered is that first of all we have seen the standard equation which is saying the total number of swaps. So it is suggesting to me how many total number of swaps are there, right? So I will be able to get an idea that at the lower level, which I can say it as n by 2 to the power 0, at this level 0 swaps are there, right? At the next level 1 swap is there, at the very next level 2 swaps are there, and this series will keep on doing until the log of n levels. So what we are doing is that we are adding everything. Now in the next step we took n as the common. So when I take the n as common, we will be able to get the first term as complete 0. I will not take care of that. Then I will be having 1 by 2 to the power 1 plus 2 by 2 to the power 2 plus, similarly here we will be having 3 by 3 to the 2 to the power 3 until so on, until the last level which is log of n divided by 2 to the power log of n. Now I want to make this as a GP series. So what I did is that I divide the above equation. So equation number 1 divide equation number 1 by 2, right? So when we did the division here, so we will be able to get s by 2 which is equals to n times. So here we did the, when you do the division by 2, so it will become 1 by 2 to the power 1 into 2. So it will be 2 to the power 2. So we will be able to get the value as 1 by 2 to the power 2. So at the denominator, we are multiplying everything by 2 by 2 by 2, right? So we will be able to get 2 to the power 3, 2 to the power 4, until 2 to the power log of n, 2 to the power log of n plus 1. So here I just have written one term which is before that. That's it. Now what we can do is that we can do a subtraction from equation number 2 to the equation number 2 with equation number 1. So we will be able to get this term. Now if you will observe this equation, here if you will see the value of a is something which is equals to 1 by 2. Now I am talking in terms of a GP series because yes, this is something which I can say is a valid GP series, where the value of a is denoting the very first element in a GP series. So if you will observe here, the first element that we are getting is 1 by 2 to the power 1, which is equals to 1 by 2 only. After that, what is the common ratio? R, which we called as common ratio. It is something which is equals to 1 by 2, because how we calculate the common ratio? The difference, the division between the consecutive two terms. I hope that all these things you already have gone through in your 9th and 10th classes, but it's my responsibility to state you everything step by step. That's why I am doing. Otherwise, I know everyone can solve this very much clearly. So it is nothing but 1 by 2 to the power 1 divided by 1 by 2 to the power 1. So here you will be able to get the common ratio as 1 by 2. If you will observe, this common ratio is something which is less than 1. Now this is the summation of a GP series. This series, here you can apply a formula of sum of GP series. When the common ratio R value is less than 1, what is the summation of that? This is nothing but is equals to A into 1 minus R to the power N divided by 1 minus R. This is something which is a formula of a sum of GP series when the value of R is less than 1. So here if you will observe, the value of R is less than 1 only. Now what we can do is that we can just apply this formula inside this bracket that I have. So this is S by 2, which is equals to N into A value is 1 by 2, 1 minus R value is 1 by 2, log of N that we will be able to get divided by 1 minus 1 by 2, right? Minus, we will be able to get log of N divided by 2 to the power log of N plus 1. Outside bracket is there. This is the equation finally that we will be able to get, right? Now what we can do here is that, here if you will observe, what we can do now is 1 minus 1 by 2 will be 1 by 2, and this 1 by 2 we will be able to cancel out with this clearly. This is fine. Now what I can do is that I will take the LCM. So I will be able to get 2 to the power log of N, 2 to the power log of N minus 1 minus of log of N divided by 2 to the power log of N plus 1. Fine. Perfectly fine. So until this part, I hope everything will be clear. Now, if you will observe this 2 to the power log of N, and please be aware that this base is 2 only. So can I write like this, N to the power log of 2 base 2? So what I did is that I just take N upfront and 2 backward. And this value is nothing but is equals to 1. N to the power 1 is nothing but N only. So what I am saying is that, what I am stating here is that wherever I am having this term, which is 2 to the power log of N, I can replace that term with the value of N. And I hope I'm making sense to everyone. It's very simple. So what I can do is that I will say N minus 1 divided by N minus log of N divided by this also. If you will observe, if I will split it, it can be written as 2 to the power log of N into 2. So I am writing 2 to the power log of N as N using this equation. I have already explained you why is that so. So into N into 2, right? This kind of derivation you can't find it anywhere. The explanation, the way I am explaining to you each and every step, I think it should be clear to everyone. In standard books, if you will go, when I went for the very first time in the standard book, I found it very much hard to understand that how they will be able to get that big O of N time complexity. But I am trying my level best to explain to you in a proper way so that each and every step mathematically should be clear to everyone. If you still have any doubt, do let me know. Otherwise, it's of no use to explain it in much depth, right? So now here if you will observe, I will be able to get this equation. Now if I will take N inside the equation, I will be able to get N into N minus 1 by N minus N into log of N divided by N into 2. So I took N inside the bracket, right? Okay, fine. So here, now it's clearly visible. N and N will be cancel out with each other. So what we will be able to get? We will be able to get the equation which says S by 2, which is equals to N minus 1 minus log of N divided by 2. Now what I can do is that I can take 2 to the right side to get the total number of swaps. So it will be equals to 2N minus 2 minus log of N. This is the final thing after which I can't solve much. So if you will see here, we will be having N, we will be having log N. We have seen a lot of times that whichever is having a big O, that is the final thing that we have to take care of. So can I say now that the time complexity requirement is something which is equals to big O of N, because the total number of swaps is something which is equals to big O of N. in worst case scenario. So that's the complete intuition behind why it's usually said that whenever we are computing a time complexity, whenever we are computing a time complexity to basically build any heap, this is something which is equals to big O of n. This is something which is equals to big O of n. And the kind of method that we are using here, or that I have explained you above, is something which we called as a heapify method. This is famous by the name of a heapify method, where what we are trying to do is that we are trying from the level above in the leaf node, and from there we are keep on exploring that whether it is following a Minheapify property or not. If not, we are doing a swaps, and how many number of swaps we are doing in worst case scenario will become the overall time complexity for that. And that's what we have find out with the help of a derivation, and we have seen that the time complexity we got as a big O of n. So next time, if suppose someone is asking to you, what is the time complexity to build any Minheap, your answer should be big O of n, not big O of log of n. If someone is asking to you, can you explain to me the justification for that, you can explain to them the complete derivation for the same which I have just shown you just now, right? Now I think it's the right time that we can discuss about the heap sort algorithm. I have already given you the gist of that, but let me talk about the algorithm in a proper sense with its time complexity aspect. So the very first thing in a heap sort algorithm says that given the numbers that we have, we need to first of all create any heap, right? We need to first of all build a heap. So build a heap. Now it can be anything. It can be you are creating a Minheap or you are creating a Maxheap. It doesn't matter. Depending upon whether you want your data in a increasing sorted manner or you want your data in a decreasing sorted manner, right? Decreasing sorted fashion. So according to that, you are building a Minheap. You are building a heap. Now we already have discussed that what is the time complexity required to build any heap. That will be equals to big O of n, right? Now after that, what we are doing? Second step is that once our heap will be ready, whether it be a Minheap or a Maxheap, let's take Minheap only. After that, what you can do is that you will try to delete all the elements, right? Step by step. Step by step. And what you can do is that you are deleting the elements, so you are getting the first smallest, second smallest, third smallest, and you can store those deleted elements. You can store those deleted elements in any of the data structure, or you can store it in the same array also which you are using, right? There is no reason to go for an outplace kind of algorithm. You can store it in the same array. So basically the important point here to understand is that we are doing a deletion for all the n elements. We already have discussed that for doing a single deletion, it will take log of n time complexity. Now when I'm saying that we are doing a deletion for n elements, it will be nothing but as equals to big O of n into log of n, right? Because for single deletion, time complexity is log of n. For n elements deletion, time complexity will become big O of n log n. So what is the overall time complexity? And that's done. If you are using any Minheap, you will be able to get a increasing order fashion. So if you are using a Minheap, if you are using a Maxheap, then you will be able to get a decreasing order fashion, right? So basically, when I'm talking about the overall time complexity aspect, so the overall time complexity will be something which is equals to the combination of these two, which is big O of n to build the min heap plus big O of n log n to mainly what we can say to delete all the elements. So what is the overall time complexity? It is nothing but is equals to big O of n log n. And this is the simple process of any heap sort algorithm that you ever see so far. But now it seems to be easy. Why? Because we already have gone through the complete process of understanding of the fundamentals of heap data structure. If I will straightforward starting with this at the very first video, you will just kill me that what you are saying, order of n build heap, order of n log n deletion. What's there? What's the thing about that? So we already have covered up our research. After that, we are coming to a conclusion. And I think this is the best way to study any of the new topic, right? So this is the overall time complexity for the same. Now I think it's the right time. In the next upcoming videos, I will talk about the implementation of all these things. We will see, because in Python, we usually have the packages. So you don't need to write the codes, but understanding is obviously required. But how basically we can use those packages, whatsoever we have studied, there is something called as heap pq in Python, where there is already a methods which are developed, right, specifically to Python programming language. So I will show to you in the next upcoming video, where I will talk about the interview based questions and how you can import and utilize these properties of heap, whatsoever we have discussed so far, by importing just the packages, and you can call that. But in order to do so, obviously the complete understanding will be required. So I hope that until so far you will be having a very good understanding of a heap data structure. What is Minheap? What is Maxheap? How basically heap sort will work? Everything in depth we already have covered up. Now the most obvious question which can be in your head is that whenever we are going for an interview and whenever we are preparing for that, do we require the implementation of all those things? Or maybe what kind of questions can be asked from you from that aspect? So see, the very first point is that whatsoever things we have covered up in our complete portion of this heap data structure, everything is very important whenever you are preparing for an interview, because these are the fundamental things that you should know. On top of that, now you will observe that specifically when you're writing a code in a Python, they have made everything easy. The developers already have written the code there. So if you will go inside the documentation of this heap pq, I would highly recommend you will go there. You will be now easily able to understand each and everything. So whatsoever concepts we have studied. So the good thing about Python programming language is that we have the packages, we have the libraries, we have the functions which we can call directly to do our task. But the bad thing is that there is so much abstraction. So see, here I am here for you to explain all these concepts. But when I studied these concepts for the very first time, it took me a long time to understand those things from the standard books. So now, once you will be able to understand those concepts, now it will be very easy for you to understand what is this heap push function. So now you know that how basically the insertion will happen in an heap data structure, or given a value, how you can insert it in a min heap. What's the complete process? You completely know that. So now you don't need to write a code step by step. If you want, you can. But I would certainly recommend that you can directly use this. You can import this heap pq package whenever you are writing a code, and whenever you are in a need to use the heap data structure. And after that, you can simply directly call these functions. For example, there is a task of insertion of an element, which you know will take order of log of n time. So you can simply call this heap push function to push an element inside a min heap. Similarly, to delete any element, we already seen the operation, we already know the concept now. So it's not like that we are just calling the function and we don't know the internals behind that. That's the important thing, that whenever you are calling any function, whenever you are using direct packages of anything in a Python programming language, specifically I'm talking about, you should know the internals of the same, right? Similarly, when we used to study machine learning or data science domain, so again, there are so many packages in Python that is provided to us. For example, in machine learning algorithms, we have sklearn libraries, right? To call the linear regression, to call the logistic regression, and any other algorithm as well. But the internals of that, but the mathematical intuition of that, you should know, right? It's not like that we are just calling it and we are doing the implementation and we don't know the internals behind that. That is the very bad way to learn anything. It's just that you are doing for the sake of doing. But what I am saying here is that you are doing for the sake of learning. So once you are good with the fundamentals, once you know that how basically things are working, and now you know about the heap data structure, how things are working, now it's not a bad idea to go for this kind of a documentation once. Take a read of that step by step, see what are the methods are there and which kind of methods you can use to do your task. For example, you want to get largest elements, you can call dot and largest function. You want to get the smallest elements, you can have n smallest function directly. And these functions only I will be using, and I am discussing today in this session as an interview question, which is very much vastly asked. Maybe in my audience or in my students, there might be a question. Please do let me know if you have faced already this question in an interview as well. So the question says, it's very simple. What it says is that suppose you will be provided an array. Suppose you will be provided an array which contains the numbers, which contains the elements. For example, here if you will observe, we will be having the values as maybe 1, 1, 1, followed by 2, followed by 2, followed by 3. Suppose this is a kind of an array that is given to me. Now what is the objective here? The simple objective is to calculate the top k frequent elements. For example, if I will say that the value of k is equals to 2, so what is the meaning of that? I want to say that give me the top 2 frequent elements, top 2 frequent elements in an array. Fine. So here if you will observe one thing, what I want to show you here is that when we see here there are 3 unique elements that we have. First of all, 1, 2 and 3. How many times 1 is repeating? Mainly 3 times. How many times this 2 is repeating? Mainly 2 times. How many times this 3 is repeating? Mainly 1 time. In total 1, 3, 4, 5 and 6. So in total, if you will observe, we will be having 6 elements. The index will by default will start from 0. So it will move towards 0, 1, 2, 3, 4 and 5. Right? So the question says you need to find out the top k frequent elements. One of the vastly asked question in an interview. Now, one thing here you will observe, if I will create some dictionary kind of a structure where this is the key, right? The unique elements that I have, and this is the value, then I will be able to find out the topmost frequent elements. For example, if I am saying that the value of k is 2, so the answer will be simply equals to, so topmost is this 1 and 2. So top largest elements according to the frequency I am saying is 3 and 2. So the output should be equals to 1, 2. So this is something which I will say is the expected output. This is something which I will say is the expected output that we are getting here, right? Fine. So this is the question that is given to us. So basically a user will provide 2 things. One is the array, another one is the value of the k. After that, it's your task to give the user the topmost k frequent elements that you have. So simply here you need something called as a frequency as the most important thing. And according to that, you will be certainly able to find out the values, topmost k values. Now, if you will try to observe here the simple intuition behind this is that if you already aware about one package called as counter inside the collections in Python, which is basically responsible for the same task, that is to count the frequency of each element in an array. This is the responsibility of this particular counter value. So to count the frequency of each element in an array. So what I can use is that I can use this particular package from the collections. I can import that, and then I will be able to find out this particular value. Once I will be able to get this particular value, what I can do is that I can import the heap pq package completely, and inside that what I can do is that if I will be able to call that n largest elements, so and I will give the value k, which is the numbers, how many numbers do I want, and on what basis? On the basis of this frequency value, which you can specify as the value of count.keys, you will be able to get the most frequent elements. So here I will try to show you the implementation so that the things whatever I am saying here will be easily conveyable to everyone. Okay, let me open the Jupyter notebook here. So top k frequent elements. First of all, what I can do is that let me write the driver code here. So in the driver code, what we can do is that we can take the array, for example, 1, 1, 1, 1, 2, 2, 2, and 3. This is a kind of an array that I have, and the value of k is equals to 2. Means what I want is that I want topmost 2 frequent elements here, right? I hope this is clear. Now what I can do is that I can call the function. So there is a function calling. So here there is a result which I am storing by calling the function top k frequent elements. So this is the method name which I am calling, and inside that I am passing the array as well as the value of the k, and I can print the result by saying the top k frequent elements are, and here we can simply say result. Now what I can do is that I can simply call the function definition here, and here we can simply define the method that we have created, right? So I can just copy this here. Now what I can say is that, so first of all we need to understand that what can be the base case condition that we can imply here. Okay, just assume that if the value of the k that you are saying is equals to the length of the array that you have. At that point of time, simply what you can do is that you can simply return the elements present inside the array, right? Because if you will assume, for example, I am saying that the array contains, suppose something like this, 1, 2, 3, and 4. And you are saying that give me the 4 frequent elements. Give me the 4 frequent elements. So at that point of time, what is the output? Output will be the array itself. So you can simply return 1, 2, 3, and 4 because that is the most frequent elements, because the value of the array that you have, which is equals to n is equals to 4, is equal to the value of the k as 4. And if they both are equal, at that point of time, you can simply return the array. Okay, so this is fine. Okay, now why I have used set? I have used set intentionally. Suppose what I am saying here is that suppose I am having this kind of structure. So you can ask this question from an interviewer, so whether he wants to repeat the elements or not. Here I am assuming that I don't want to repeat the elements, and set is a kind of a data structure which will not give us the duplicate elements. That's why I am using that. If interviewer is saying that he doesn't have any issue in terms of repeating the elements, then you can simply return the array as well, right? It depends on the use cases. So for example, here I am saying that I'm having this kind of a structure. Okay. And here again, I am saying that the value of k is equals to 4. So when the value of n is equals to 4, here also n is equals to 4. And I am saying that the value of n and the value of k is equal. So what I am saying is that in this point of time, I don't want to repeat the elements. So it will just print me the value as 1, 2, 3. Even though I am asking the topmost 4 elements, I am getting the 3 elements, which signifies to me that there is a 1 element which is repeated here. So these are the 3 unique elements which are the topmost frequent elements in a way. That's the simple, I would say, intuition behind writing that, right? I am side by side telling you each and every intuition, whatever my mind is thinking as of now. And that is what you should know whenever you're writing your code as well. Okay. Now, if this is not the case, if suppose this is not the scenario, then what I want is that I want to use that counter. So what I can do is that I can say from collections, first of all, import counter so that I can use that, as well as I want to import the value of heap PQ. Okay. Now what I can do here is that, I can use one variable now simply called as count, and I can call that function as counter. So this counter function, what it will try to give to me, it will try to give me a dictionary. So this results to me a dictionary where if I think show you as well. Let me return a count. Let me show you basically what this count will return to us. Okay, so can we print that? Let me print if I will be able to get something out of it. No. So here I think I will be able to print by specifying the keys. So I will show you that thing. So basically what I'm saying is that this counter will be able to give us the key value pair, where key is the unique elements that we have and the value is the frequency of that element. I will show you, just wait a minute. Now basically what I am doing is that I am saying basically what I want is that I want the top largest element. So what I can do, heap pq dot n largest. In this way I can show you the values. So here I am specifying how many number of largest values I want, k values, right? Here if you will say, I will say count dot keys. So if I will call this, I will be able to get the output. I should be able to get the output now. So I can return this statement. So here if you will see, I will be able to get the topmost k elements, which is having a high frequency. Now, why it is not returning anything? So here, it should return. Oh, we are not passing any array. How it will return? Okay, now I think it should be fine. Yes, but output is not fine here. So here we will be able to get the count. Fine, let me print the value of the count. What is the value of the count I am able to get here? So this is what I was telling to you at that point of time. It is just giving me the value key as the 1, 2 and the 3, and the value as the number of elements, the frequency 4, 3 and 1. So what we can do is that we can pass one more parameter key, which is equals to count.get. Okay, so now here if you will be able to see, in n largest, we will be having the 3 parameters. If you will observe the documentation, let me try to redirect you again with the documentation part. This n largest will contain the 3 parameters. Although this key is equals to none is a optional parameter. If you want, you can define. If you don't want, it's okay. It's completely fine. Let's try to understand what are these 3 parameters all about. First of all, this n is something that how many number of elements you want to print from your data set that you have. So here, this value of n is something which is for our purposes k, that I want to repeat, I want to display the k largest elements present inside my dictionary. Then iterable is something on which particular value you want to iterate. So there we have defined the count dot keys value. And what is the key? So what is key here? Basically, if you will observe, key is something, it specifies a function of one argument that is used to extract a comparison key from each element. So what is the point where you want to do the comparison? So I want to do the comparison on the frequency portion. So that is what we are defining in our code. So now here, if you will observe, clearly we will be able to get that, okay, on this particular parameter I want to do the comparison and give me the topmost two values. So here, if you will observe, it will be able to give me the output as 1 and the 2. If suppose I will change it to 3, let's see what will happen. Now here, if you will see, you will be able to get the value as 1, 2 and 3. Correct? That is something which I want to show you. So this is the simple, I would say, method to basically find out the topmost k frequent elements. Here basically, if you will see, the logic is very simple. The one thing here which I did mistakenly is that we have to use the add. That's why at that point of time we are not getting some output. If you remember when I was showing to you. Anyhow, now here if you will observe, once you will enter this, so you will be able to get a point that this count is nothing but is a dictionary now, which contains unique values as the key, and if you will observe, the frequency of those unique elements as the value. That is the important thing, and that I have just displayed you also. If you want, you can just remove this, because the major purpose is not to go into that part. It's just for those who are not aware about this this method. The major purpose is here to get that largest topmost frequency, right? So here, that is something which we will be able to get using this method. I hope that now you will be able to see that here we are utilizing the property of heap data structure, and how basically we will be able to utilize that. That is a very crucial point to understand here. The important objective here to show you these interview based questions is to make you familiar that there exists directly this documentation where you can directly use these methods of heap data structure, which we just have studied in our previous classes, right? Whatsoever concepts we have studied, you can directly use that by just calling one method here. We do have all these methods. So I would suggest everyone to go towards that standard documentation as well, which I just showed you, in order to utilize those functions, so that if in future you are using, if you are facing these kind of questions, you can directly use these functions by just importing the values of heap PQ. This is again a very vastly asked interview based question. I hope that maximum students also have encountered this problem for the first time in an interview. And if those who have not encountered yet might encounter in your upcoming videos or in your upcoming interviews, right? So let's get started. First of all, we will try to understand the problem statement. Afterwards, we will try to see the logical understanding of the same, that how we can approach towards this problem. And then after that, I will do the live code implementation for the same. Fine. So the question says that you have to find out the k closest points to the origin. For example, here we will be having a 2 dimension. If I will try to create here, it's an x-axis, right? It's something which we can say is a x-axis, and this is something which we can say is a y-axis. This is the origin, right? Now, if I will try to plot the points, so obviously +1, +2, +3, something like this will be here. Here it will be -1. We all know, right? -2. This is how things are there. And similarly, here it is positive x-axis, 1, 2, 3. And this is negative x-axis, -1, -2, and so on. So, for example, these are the points. I'm just taking a random example like 3, 3. So, this point will certainly lie over here, right? Then we will be having 5, -1. So, suppose here it will be 4, it will be 5. So can I say that 5, -1 will lie maybe here, right? And then I will be having -2, 4. So when I'm saying -2, so 4 is suppose here. So -2 is here. So -2 comma 4 will for sure lie over here. So this is a kind of a space which is given to you where you will be having the points. Obviously the first point is referring X and the second point is referring Y in the points dimension. That's perfectly fine, I hope. Now, here if you will try to observe, what is origin? Origin is nothing but, we all know that origin, whenever we are saying, it is nothing but 0, 0. Means this is the point which I can say is the origin, right? Now, by taking a distance measure, they have clearly specified that you can take a distance measure which is something equals to Euclidean distance. I hope everyone knows what's the Euclidean distance. So those who are not aware, let me tell you. So they are saying that you can take a Euclidean distance as the distance measure. So Euclidean distance formula says that if there is some point P1 whose dimensions are x1, y1, and then there is some point which is P2 whose dimensions are x2, y2. So according to Euclidean distance, the distance will be equals to square root of x2 minus x1 whole square plus y2 minus y1 whole square. This is the Euclidean distance formula to measure the distance between the 2 points. Now, one point will always be in this particular question for you is the origin. So if one point is origin, maybe consider that P1 will always be origin. So it will be always 0, 0 in your question, right? This is the standard formula. This is something which I am saying is the standard formula. Now for our question, what they are saying is that we have to measure from the origin. It means that one point will always be 0, 0. So at that point of time, consider the value of x1 and the y1 to be 0. So our formula will become, you can say square root of x2 square plus y2 square. So whatsoever be the points you have, you can do the squaring of that, addition of that, and square root of that. Now, whichsoever be the minimum, you will be able to get. So what we need to do here is that, in a way, I am now talking about the intuition. So if you will observe according to this question, we need to find out first of all the distances of this with respect to the origin. We will try to store those distances in, can we use Minheap here? So see, whenever we are talking about minima or maxima, you can always think of this kind of a data structure, because Minheap is famous for finding minimum element, Maxheap is famous for finding maximum elements, right? So what I can do is that I will try to create one Minheap which basically contains two things. One is the distance of each and every point from the origin, followed by its corresponding points. Why I am storing this corresponding points? Because as in final output, if you will observe, you want points. You don't want the distance to be printed, you want the points to be printed. So what you can do is that you can create a Minheap which contains both of these things. At 0th index, you can store the distance. At first index, you can store the points. Now, when you will create one Minheap according to this particular kind of a structure, which is in the form of a list, you will push the elements having distance and the points. What you can do after creation of that, you can start deleting the elements from the Minheap. Means you will apply the pop operation, heap pop operation, until how many number of times? Until k times. So when you will apply the delete operation until k times, you will get the top k minimum distances. Very easy, right? Top k minimum distances you will be able to get very easily. And for those top k minimum distances, you can fetch the list corresponding to the first index. So this is 0, this is first. So you can simply print only the points here. And that is what in your question you want to do. That is what you want to do in your question. So this is the kind of a approach that we will follow in our implementation part as well. I hope that the approach is pretty much clear to everyone. Now how we can do the implementation? It's very simple. If the approach is clear, implementation wise, everything is very easy. Let me try to again open the Jupyter notebook. So this is what we want to find out, the k closest points here, right? We want to find out the k closest points. Let me rename it. So what I can do here is that, let me first of all write the driver code. So inside the driver code, if you will see what are the points that we have, first of all, I need to write that particular thing. So let me go back. I will take the same points 3, 3, 3, 3, and then we will be having 5, -1, 5, -1, and then we will be having the third point as -2, 4. Now here if you will observe, one thing that we didn't discuss is the output. What is the 2? Now here if suppose in our question we are passing the value of k as 2 and these are the points that we have, what is the 2 nearest topmost nearest points? We can clearly see, right? When we're talking about 3, 3, this is the point which is the nearest one to the origin. And the second one is when we are talking as -2, 4. So if you not using visualization, you can simply find out the Euclidean distance using the formula which I have shared with you. You will observe that these two are the nearest point. So this is the expected output that is expected from you. Order can be varied, but these 2 points should be the output that we should get, right? If our logic is correct. Let's get started now. So here if you will see, k is equals to 2 that we are displaying. So points is equals to, these are the points that we have. Now whatever be the result, we will be able to get. I am storing in variable top. So k closest points we want to display, or you can simply write k closest as well. Here you can mention the arguments as points and the k that we want to have, which is entered by the user. Now what we can print is that we can say that k closest points to the origin are, so this statement you can print if you want, and here you can display the result whatever you are getting. So this is something which I can say is the function calling that we are doing here. Now obviously when we are creating a min heap, we need again the heap pq function. So what you can do is that from heap pq complete package, you can import the functions which we required, which is heap push and the heap pop. These are the 2 functions mainly that I required to do the implementation. Now one more thing which I want is the math library I want to import, because I want to do the square root to find out the Euclidean distance. Okay, that's completely fine. Now I think it's the right time to move ahead towards the function definition. Now here what I can do is that I can define the function named as k closest. I can define the function k closest, which will be having the points and the value k. Fine. Now here what I can do is that, first of all, let me extract the value of n, which is nothing but the length of the points that we have, because that many times I will make a for loop. What is the value of x, by the way? Here the value of x is nothing but is equals to, what is the points? So what you can do is that you can make one for loop for I in range until the value of, I would say, n. We will iterate. At each and every time we need to extract the value of x and the value of y. So the value of x is nothing but points of I, inside that the 0th index, right? And y will be equals to points of I, and in that we are saying the first index is equals to y. Perfect. Now what we want is that we want to create one min heap. So what we can do here is that inside this function, we can create one list which will be responsible to store those elements of the min heap. So what we can do is that we can simply apply heap push. Inside that, I want to push the min heap. Inside min heap, I want to push two elements mainly. One is the distance. So this function will be responsible to calculate the distance. I will define that function. Apart from that, I will also store the points of I. I think this is completely fine now, right? This is completely fine now. So now here, if you will observe, we will be able to store the values of the min heap. What are those values? We are saying store the distance and the points. Now what we can do is that we can define the function which we have just called here, get underscore distance. Otherwise, obviously it will show the error. So what we want is that we want to just return math dot square root. What is the value of x square plus what is the value of y square. I think this is pretty much fine to everyone. Okay, now our min heap is created. Now what we want is that we want to display the result. So the result is something which will be a list which will basically store the points which will be having a minimum distance. So until how many times we want to make a for loop? Until k times, right? We want k closest elements. And inside that, we can call the function, namely heap pop, on what particular thing you want? On min heap, right? Min heap. At the first index I want to display because I want only the points of I. And I will append this inside the list. So you can call this function named append. Simple. And finally, once I will be out of the for loop, I can simply return the result here, right? This is fine. I think we are good to go. Let's try to see what are the things we are getting. If there is some error, we will try to resolve it at that instant itself. Perfect. So here, if you will observe, when I am saying k is equals to 2, it is giving me the output as 3, 3 and minus 2, 4. This is what we are expecting, right? This is what we are expecting here. So here, if you will observe, simply what we are trying to do here is that we have used one function. So get distance function is responsible, is basically helping us to calculate, to give the Euclidean distance. So this is what you need to define because they have already mentioned that on what basis the distance will be evaluated. And after that, this k closest will be simply helping us to find out the closest elements. Here, if you will see this heap push function, which we are directly using here, is responsible to insert the elements inside the min heap. And you all know that how basically the insertion will happen inside the min heap. And similarly, when I am doing a pop, so this heap pop function is responsible to delete the elements from the min heap. That's the important thing and the key takeaway that you need to take from this session. How basically inside the min heap we can do the insertion as well as the deletion, right? And then you will be easily able to get the approach. I hope approach wise it's quite easy to understand. So that is the overall idea behind finding out the k closest elements with the help of this approach. Now your assignment is to tell me that what should be the time complexity required to obtain this task, because you know what is the time complexity to do the insertion, you know what is the time complexity to do the deletion. So you should tell me what do you think is the time complexity required or time complexity for the below mentioned code. Let me know in the comment section. I will for sure see the answer of everyone, and that answer will tell me that whether now you will be clearly able to understand this module of heap data structure or not, because in this particular code I am using the insertion, I am using the deletion, I think everything I am using here. It's a very good question, I would say. So do let me know in the comment section, and I hope that now the concept of heap data structure is pretty much clear to everyone. So with this, I would like to end this particular session. I hope that you enjoyed this complete series of heap data structure. With this, happy learning to all. Bye-bye everyone. See you soon in my next upcoming video.